Okay, thank you for the organizers for having me over. It's always a pleasure to visit. So yeah, Scott and I are going to talk a little bit about this paper that we wrote a few years ago. And because we wrote it a few years ago, both of us kind of forgot what's in it. But there are other people in the audience who know this much better, so you can ask them. Okay. So in his lecture, in his first lecture, I think, Greg Eink already mentioned the passive transport equation. So let's write passive transport. So just a transport equation. U is a given vector field. It's incompressible. I don't know. Is it working? And please interrupt as much as you like. There's some initial data, which I'm just going to label somehow, theta initial. And okay, so kappa is a positive number. It's molecular diffusivity, or if you go non-dimensional, it's inverse Peclet number. The initial data we're going to take to be, okay, so the problem is posed on the periodic box. So X is on the periodic box. T is, let's say, on any finite time horizon, it doesn't matter, 0, 1. And of course, because U is divergence free, the mean of this will be conserved so that we don't always have to subtract the mean in every single statement. Let's just take initial data so that the mean over the box is 0. And you can think of the data as being smooth if you want, C infinity. But it shouldn't really matter. Okay, so then what is U? So Greg already mentioned the physically relevant problem. You are meant to solve whatever, maybe Navier-Stokes at high Reynolds number or something like that. You get a turbulent flow. And then in that turbulent flow, you put a passive tracer like dye or something. And the effects of the tracer on the flow are neglected to leading order. So this is not Boussinesque or something like that. It's just a drift diffusion, okay? And you just want to, given this quote-unquote turbulent vector field, you want to see what happens to the solution, either in the limit as kappa goes to 0, or at least for kappa very small, okay? Not very importantly, however, that kappa will never equal 0. It's always positive, but you should think of it as very small, and you guys know this better than I do. What are the relevant ranges of Peclet numbers that you may care about? But if Schmidt number is unity and you care about very large Reynolds numbers, you're going to have very large Peclet numbers. Okay, so the question is, what happens as kappa goes to 0? And in order to talk about this question, I'm a mathematician, unfortunately, so I need to have very precise definitions of everything. So first of all, what is a solution? What kind of solutions are we talking about here? And the vector fields that you care about in turbulence maybe are, you extend the inertial range of a turbulent flow to infinity, because maybe you're thinking that the Reynolds number goes to infinity, or, better said, that you want to assume something about U which is going to be uniform in Reynolds number, okay? So you should have the regularity that you would expect in the inertial range. And in a turbulent fluid, that's 1/3 regularity, right? Onsager, Kolmogorov, 1/3 regularity. So let's say throughout the talk that we're going to look at solutions which are continuous in time and C alpha in space. But of course, the number alpha, you may think of it as a third, if you want, for everything I'm about to say, but of course, we don't have a theorem for a third. So I'll say more about that later. So here alpha is going to be positive. And it,
just to make sure, so the U does not depend on kappa, the U is fixed.
U is given in advance. You have a turbulent flow, a turbulent realization, and then you put a tracer in it. Okay. So in this type of regularity, there's a unique sense in which you can talk about solutions of this. Solutions are unique, they're strong. In positive time, they experience parabolic regularity. This is a parabolic PDE. So in positive time, the solution is going to be C2 alpha in space because of this. It's going to be C1 alpha over 2 in time due to parabolic smoothing. So in positive time, even if your data is rough, the solution is actually very smooth. If your data is smooth, the solution is even smoother. Okay? So we don't talk about weak solutions. We're not worried about any kind of devils at positive kappa. Everybody is smooth. So in particular, because everybody is smooth, you can do the formal computation that you would always do when you try to compute energy, quote unquote. So I will denote the L2 norm at time t. I will unfortunately sometimes call this the energy, but of course it's a passive tracer. Energy doesn't make any sense. I should really call this the variance of the tracer. Okay, that's the correct statement to make because it's zero mean, right? So we assume that it's zero mean. By the way, if the data is zero mean, that the solution has zero mean. That's obvious. So this is really the variance of the process, but I will, please excuse me, I will also use the word energy, okay? Just because.
Sometimes called intensity.
Intensity. Thank you, Greg. And so you write down, because you have well-defined unique smooth solutions, you can write down the balance, the intensity balance, if you want to call it like that. And how do you get that? Well, you just multiply this by theta kappa and you integrate over space. When you multiply this by theta kappa and you integrate over space, because you use divergence 3, this term is going to die, and you just get that theta kappa at time t plus the dissipation of energy is equal to the initial data. And as opposed to, let's say, Leray-Hoff weak solutions of Navier-Stokes, where you can only write this with less or equal, here you write it with equal, because the solutions are smooth. You don't have to worry about anything. Okay, so this is really an equal sign. And this, in principle, gives you the an a priori estimate, which is very good, but of course, you immediately notice that you also have the maximum principle. If your data happens to be in L infinity, then just by the maximum principle, you also have an L infinity estimate a priori, okay? Because in the end, we're going to want to do this for data which may not be in L infinity. We're not going to use this maximum principle at all, okay? So this is not the only a priori estimate, but it's the one that we're going to rely on. So in particular, uniform in kappa the only estimate that you get from here is something which is L infinity in time with values in L2. And that's pretty much it for this one. What can you deduce from this bound? Well, again, this was already mentioned earlier, but let me just say it nonetheless. From Bana-Haloglu, you get that there exist subsequences kappa n which go to 0, and along those subsequences you have weak star convergent limits. Okay, so the a priori estimate implies that there exist subsequences and along those subsequences converge weak star to some object theta bar in L infinity L2. And because the equation is linear, automatically you get that whatever that limit point is, it is a weak solution of the transport equation. So what does that mean? It means it solves this in the sense of distributions. Okay, so
Didn't you just promise there wasn't going to be any weak solution?
for positive kappa, there's no weak solutions. I mean, they are, but they're unique and they're particularly strong. And I will never, ever work with this, just because it gives you the wrong intuition. Okay. Now take one of those sequences, take one of these limiting objects, and look at the energy balance, and just slap a limb soup on the left side of the energy balance. So okay, you get this. So I'm just placing limb soup on this, okay? Of kappa okay, so this is of course equal to limb soup initial data L2 squared minus the solution at time t. Okay, I haven't really done anything. And now this doesn't depend on kappa, so I can put this in here. Limb soup of a minus becomes minus of the limb inf. And now you know that in weak limits, limb infs can only drop. Okay, that's a standard statement. So in particular, this and now comes the first inequality. This is less or equal this. Okay, so here I'm being a bit imprecise. I should really write this lim inf along that subsequence, okay? So please allow me not to write that subsequence. Okay, so this is just a simple exercise in the triangle inequality, but it has a consequence. And the consequence is the following. This object here is always non-negative, and it's bounded from above by something. So if, for some reason, you know that the solution of the transport equation that you got in the limit there conserves its L2 norm, then the right-hand side is also equal to 0. Okay, so it keeps going. Great. So if any weak solution of the transport equation conserve in time, right? It's L2 norm. Then the right-hand side of the top inequality is 0. Then 0 is less or equal to this. Now, you notice I wrote and I've underlined the word any. A priori, you don't know that the transport equation has unique solutions. So to make this, to go from the very far top board, whoa. Oh, no, not this one, sorry. To make any useful prediction from this inequality here, you need to know that no matter what theta bar was, if it conserves its energy, then you get 0, okay? But I want to emphasize this is not a statement about uniqueness of solutions of the transport equation. This is a statement about the fact that they conserve L2 norm. These are very different things, okay? So basically, when does this happen? Well, the standard example is the Cauchy-Lipschitz theorem. And so basically, if U is L1 in time and Lipschitz in space, and it's continuous in space-time, all my vector fields are going to be continuous in space-time. Then not only do you have that all solutions of the transport equation conserve the energy, there's just one of them. That's the Cauchy-Lipschitz theorem. And there's one solution, and it conserves its energy. But of course, you have diperna ions. And they basically say that, okay, if U is L1 in time and W1P in space, so let's say W11. So if the gradient of U is not bounded in space, but it's just integrable, then all weak solutions of the transport equations are renormalized. That's a statement you can prove. Then you can, their theorem is that renormalized solutions are unique within the class of renormalized solutions. And in particular, they must conserve their energy. Okay? So the consequence of these two statements is that if the gradient of U, the space gradient, is in L1 in space-time, then this is true. Okay? Then energy conservation in the limit Now, of course, the vector fields you encounter in a turbulent flow are not going to have typically this regularity. They're not going to typically have a gradient that's bounded.
Maybe you could explain us the difference between WS1P and C alpha shot that you expect from Anomalous?
Yes, of course. Of course. So W1P is just the closure of C infinity functions on periodic box. Okay, so I'll just write the norm, okay? Right, so it just means that U is in LP and the gradient is in LP. Okay, if you take it to be zero mean, Poincaré says the gradient controls everything. Okay, so C alpha so you have the L infinity norm plus the C alpha semi-norm. And again, if you have zero mean and you're in a periodic box, only the semi-norm matters. They scale in a different way, right? So this norm, which is the equivalent norm on W1P for zero mean functions, scales like -1 plus dimension over P. And this one scales like minus alpha. So if you rescale the function, you blow up, and you look at the exponent of the blowing up parameter. And of course, the Sobolev exponent tells you when these two are equal, right? So if dimension is larger than P, there always is a positive alpha so that the Sobolev exponent holds. But in turbulent flows, you basically have, so this is the Sobolev theorem, okay? This, right? You don't want to do that. In fact, in spite of the fact that they scale in the same way. So basically, in turbulence, right, you think of alpha as a third, and yes, you can think of a p such that this is an equality, right? And there will be a p. So you may think, oh, but then it's different. It just doesn't work. The embedding doesn't work like that, okay? I don't know if this answers the question at all. Okay. Okay, so basically, so U in C0 times C alpha space does not satisfy these assumptions. Typically doesn't satisfy this assumption. Okay, so because it doesn't satisfy it, you have to allow for the possibility that the right-hand side is not equal to 0. And if the right-hand side is not equal to 0, you have to allow for the possibility that the left-hand side of that inequality, the object in the box, is not equal to 0, right? And that's the definition. So definition, anomalous diffusion. Okay. So I'm not going to write everything down, but I'm going to say some things in words. So we say that the passive, the advection-diffusion equation with a vector field U experiences anomalous diffusion if, for any initial data of 0 mean, smooth. You can take it smooth, but you don't have to, okay? But it has to be for all, right? So let's say, just to be precise, let's take them H1. This will be enough for our theorem. So this just means that the gradient is in L2, okay? So if for any initial data, what should I say about time? Should I fix a time or should I say for all time? I don't know. Time is 1, yeah. Okay. There exists a number rho, positive. It could depend on the data such that let me write t though, okay? So then this depends on t. So if I write t, then this, so rho is a function of initial data a priori. A priori, it's a function of the initial data, of some norm of the data, and of t a priori, okay? But if time is 1, it only depends on the data. Greater than rho times the initial data's L2 norm squared. And the point is that this rho is not allowed to be 0. So you have a lower bound on the energy dissipation rate, which is uniform in kappa, okay? And of course, this number rho can't be more than a half, right? Because if it's more than a half, it would violate the energy balance. It's really like that. Okay, so that's the definition. Now, of course, if we go back here to these subsequences along which you have convergence, okay, you can also define for those subsequences along which you converge a measure, a time energy dissipation measure. So you can define, what should I write? Let's say, should I write it 0 to 1? Yes. Yes. So you can define a measure E of dt, which is a limit as j goes to infinity of kappa j along any kappa j along which you have convergent subsequences in L infinity L2. Okay, so you may get a priori different measures for different subsequences. Okay, so you can just define this measure, and then of course what's written there is just the integral of this measure. Okay, So for instance, time dissipation at time 1 is equivalent to the fact that this is positive, right? Right. That's what it's written there. Okay. So anomalous dissipation, diffusion. It's like that. At time 1. If you want time t, then pick a different upper limit of integration. I feel like there's a question. No? No? Okay. All right. So these are definitions so far. Nothing. Are the definitions clear? And please correct me if I screw up. Yeah, for sure will.
The physicists would say anomalous diffusion is when the scalar dissipation goes to a finite limit when kappa goes to.
Right. So here I'm assuming something slightly weaker. I'm not postulating that there is a limit, but just that it's bounded from below.
Okay.
Which
can oscillate.
in principle, but it's not gonna, because along subsequences it actually will converge. Right. But it's this issue that you always have. Do you mean for the entire kappa? Do you mean along subsequences? Do you get different things among different subsequences? There's this ambiguity. And to fix this ambiguity, we could just write what is written on the board. Because I don't want to talk about subsequences. Okay. So what should you expect anomalous diffusion? And of course, you guys know this better than I do. The answer is yes. And my understanding is that this is considered a fact in a passive scalar advected in a turbulent flow. So mathematicians love experimental facts because that's the only thing we can hope to prove ever. Stuff that physicists disagree on, we have no chance. So only stuff that all physicists agree on, we have a chance of proving. And the goal of our work with Scott was to basically give some kind of example of some kind of synthetic turbulent flows, U, which have a lot of the properties that you would see in a real turbulent flow, and for which anomalous diffusion happens with some extra bells and whistles. Okay, so it's not just what's written on the board, there's some extra bells and whistles. But you can make, in principle, a statement which is just like that is a mathematical idealization of an experimental fact. You can make a mathematical idealization of this prediction of Obukhov and Korsin. So again, I'm preaching to the priest here. So Obukhov and Korsin, of course, independently from scaling, essentially, considerations, a la Kolmogorov, predicted that if the vector field U has some kind of limited regularity and the passive scalar has some kind of regularity that's in matching to it, then you cannot have anomalous diffusion. And exactly at the end, you should have anomalous diffusion. So let me write this down. Okay, so there's a dichotomy. Part 1. And the way I'm stating this dichotomy is the way that a lot of people have been stating this other mathematical idealization related to the Onsager prediction of 1/3 regularity implies energy conservation. Okay, so I'm going to state it in the same way. If U is in C alpha, and by C alpha, of course, I mean C0 times C alpha space, is divergence free, and if this sequence is uniformly bounded in L2 in time, C alpha bar in space, with alpha bar bigger, strictly larger than 1 minus alpha over 2, then there is no anomalous diffusion. So you notice this is exactly with an equal sign would be the Obukhov course in prediction. That would be when 2 alpha bar is exactly equal to 1 minus alpha. So if you take real fluid turbulence with alpha is a third, you plug a third here, you get 1 minus a third is 2/3 divided by 2, you get another third, right? So the prediction would be that if the flow is a third, then the vector field has a third regularity, right? But you notice I've put the strictly equal sign, so if I put a strictly larger sign, so if I put strictly larger, there cannot be anomalous diffusion. And part 2 would be that, okay, by the way, I'm supposed to give the talk, but can I ask something the audience? Is there any experiment of course it cannot be a fluid, in which you see something like turbulence, but alpha is not a third?
In 2D, it's smooth.
No. I mean, let's take 3D something, and it's turbulent.
Well, in 3D turbulence, alpha's not.
It's not exactly what
That's not what I mean. Is it possible to get a 7th, or is it possible to get 7/9?
Yeah, and if you look at flows like gravitational rotation, it's no longer
But that's just because it's anisotropic. It's not because, in longitudinal and transversal directions, they will be different, I agree. But in one direction, it's still going to be a third.
maybe it's third.
No, but is there some other object like liquid metal or something in which you don't get a third? I mean, if anybody should know, it would be this audience. The fact that you don't know.
Liquid metal and MHD turbulence also is supposed to have something close to a third, although it's got, then if you have a magnetic field, you get different scaling transverse and longitudinal.
So do you then know why Obukhov and Korsin ever considered alpha not a third?
No.
Okay, because I also don't know. I'm puzzled. Okay. Anyway.
So, then if I understand correctly, if it's alpha in space, a turbulent velocity field should be alpha in time too.
Yes.
Yes. Okay.
Yes. Okay. So now you're asking interesting questions about PDEs. So if U is C alpha in space, not in time, and it solves Euler or Navier-Stokes, but let's say Euler because it's slightly worse, then it's automatically the other way around. This is a little exercise you can just do. It's automatic. You don't even have to write it. The other thing is an open problem. I think it's not true, but I am not aware of any counterexample. It just cannot be true, basically, the other way around. So this is a strict, I claim that this is a strict thing, which is...
That thing has a name?
No, it doesn't have a name. I mean, the arrow which is true, it's just an exercise. You can just do it.
Is the other arrow true?
It doesn't matter what the dimension is. It has to do with the fact that in the other arrow, you're given the fact that the Lagrangian flow particles are in time C1 alpha, but in space they're just continuous. And by just looking at these tracers, you are asked to compose a volume-preserving homeomorphism. So I don't know if there's any people from PISA here, but if they would be, they would tell you that, wait, that's a problem, right? You can't just compose vector fields by watching tracers, because there's horrible zero measure sets on which horrible things happen. And so that's why the other thing doesn't work. Anyway, so of course, Laurent, in everything I'm saying, it's both space and time, always. I just wrote one because I'm lazy, but I know. You never measure that. You measure the increments in time of displacements of Lagrangian trajectories. You square that, you take the mean, and you watch that it's exactly going like t. That's what you do in an experiment. It's just, I think it's just completely unrelated to Euler in the class of weak solutions. Anyway, that's a separate matter. The other part of dichotomies would say the following. For each alpha in 0, 1/3, so here alpha is 0, 1. There exists divergence-free vector field U in C alpha. Such that the advection-diffusion equation in U with vector field U experiences anomalous diffusion in the sense of that definition, so in particular for all initial data. And with a time dissipation measure, so what would you expect in an experiment? You would expect that this time dissipation measure would be absolutely continuous with respect to Lebesgue, because that's what would correspond to statistical equilibrium. Okay, maybe it's not absolutely continuous, maybe it's a bit rough, right? But at least it should be non-atomic, right? The dissipation doesn't just happen at selected times, right? We could maybe all agree on that. Okay, so it doesn't have, it's not just Dirac masses in time. You know, it's not that there's some clock and then when the clock goes off, you dissipate energy and then at all other times you don't. I don't think this is how turbulence works, but please free to correct me. Okay, so that's a dichotomy. Part I is a theorem. It just follows from the old paper of Constantin E. and Titi. You just repeat their argument not for Euler, but for passive advection diffusion, and you get the answer. Okay, it's the same proof. Part 2 is an open problem. We don't know how to do that. You notice that I have left on purpose the exponent 1/3 alone, and the reason is that I actually don't know what to expect. So I don't want to, I basically don't know what to think at the end.
If it's atomic, it makes it easier to prove.
I'll talk about that, yes. Okay, so the goal would be to prove part II.
You want to put the scalar in C1 too?
Oh, thank you, Scott. Thank you, Scott. Okay, yes. So you need anomalous diffusion, you need, oh, thank you, I forgot the most important part. And this guy is uniformly bounded in L2 in time, C1 minus alpha over 2 in space. So the passive scalars, they have the regularity predictive from the scaling argument of Obukov and Korsin. Okay, so you need 3 things, not just 2 things. And notice, I don't want to give up epsilons, maybe. just the same, okay? All right. So Scott and I, we basically started to work on this, and the goal, the lofty goal is to, at some point in our lives, prove double I, okay? That's the goal. We don't have it yet. So what these lectures that we're going to give are going to be some progress towards these questions, but most importantly, I think that, and this I learned from Scott, that the correct perspective to analyze these problems, for a long time they were analyzed by looking at the underlying transport equation and studying mixing properties, and then trying to infer from mixing properties of the transport to lift those properties up to the level of positive kappa and say something. And I'm now convinced that that is not the correct perspective. This is not, because U is not smooth, this is not a perturbation of the transport equation, okay? So, and what I learned from Scott is that in the correct perspective is really to think about this anomalous diffusion like a backwards cascade of diffusivities, and this is an old idea in homogenization. I guess, Scott, would I be correct in saying that the first homogenization paper is building an eddy viscosity out of something?
No.
No?
But we found that this was in the 19th century.
Right.
So,
Okay.
so it goes back. We opened Frisch's book.
Yes.
And it says that it describes the exact idea and it attributes it to Sam.
Saint-Venant, yes. Frisch attributes it to Saint-Venant. I'm not.
1849.
Okay, so I hope that from these lectures, at least that's the thing that comes out, that it's giving you a perspective of how to think about the problem, at least, even if the results we have are not optimal yet.
So you go for the double I, it's a theorem when you replace the passive scalar by the velocity field. Why is it more difficult for the passive scalar?
What do you mean it's a theorem when you replace passive scalar?
So if for the dissipation, it's not a theorem?
No, so that's a theorem for Euler. But here it's positive kappa, and kappa goes to 0. There's no such theorem for Navier-Stokes goes to Euler. Right, so here it's the advection-diffusion equation with vector field U as kappa goes to 0. Maybe I should add the very important statement that these teeth as kappa goes to 0. And there's no such theorem for Navier-Stokes. There is one for Euler. Oops. That's a very good point. Thank you. Okay, so what are previous results? And when I say previous results, well, previous results about what? So there's 3 bullets written there. So we might as well, at the beginning, just talk about the first one. You know, construction of vector fields that give you anomalous diffusion, right? And that's the famous thing that Krajnan did in the 60s with the Krajnan model with synthetic Gaussian field, which has white in time correlations and correlations in space that are colored like Kolmogorov turbulence. And Greg already mentioned that within the Krajnan model, you can prove essentially everything, right? Everything you want. So let me not repeat the Krajnan model story because Greg already told you. Greg also already alluded to some other examples which are deterministic. So let me start with those. So Scott and I got into this business when we read a paper of Theo Drivas and collaborators, Elgindi, Iyer, and Jong. So there are 4 authors, Drivas, Elgindi, Iyer, and Jong. And in this paper from 2018, I guess, They gave an example of a deterministic vector field, which is C alpha in space for alpha less than 1, and for which anomalous diffusion happens. And this is how they did it. They took the interval 0 to 1 and split it in half. So I'm telling you the construction of the vector field U. So from 0 to 1/2, they just did a shear flow like that, okay? Okay, not discontinuous, sine, let's say, but a shear flow like that. Okay. Then they split this again in half, the remaining piece, so from 1/2 to 3/4. They did a shear flow like that. The arrows are shorter, but the frequency of oscillation is larger. Okay? Then they split the remaining piece into this. They did a shear flow like that. Arrows are even shorter, even higher frequency in space. And then you keep going dyadically. So in every dyadic interval of the type 1 minus 2 to the minus n to 1 minus 2 to the minus n, should I write +1 or -1? In every dyadic interval like that, they add a shear flow whose amplitude is left-right, depending on whether n is even or odd. Its frequency of oscillation is 2 to the n. So it's sine of, let's say, 2 to the n y. This is the stream function, let's say. And this, if you do it like that, will just be continuous. It's not going to be in C alpha. So if you want it in C alpha, you put a 2 to the minus n alpha there. And now you concatenate these. Okay, so that's a stream function, right? So the next stream function is going to be with x instead of y. And if you concatenate this, what you will discover that this vector field is, it's of course smooth on the open interval 0 to 1, but uniformly up to 1, it's in L1 in time, C alpha in space. And so it's exactly at the edge of the Cauchy-Lipschitz theorem, right? And for this vector field, what they get is that anomalous dissipation happens, and the energy dissipation measure is a Dirac mass at time 1.
For special data.
For some initial data. So they prove that there exists data, theta initial, such that this is a rho positive, such that exists rho positive with the energy dissipation measure is rho times the Dirac mass at t is equal to 1. And the proof is beautiful. I encourage you all to read it. It's just a few pages. It's really a beautiful proof. I think it should be taught in textbooks.
Why is it restricted to some data? What kind of data can escape?
So they take initial data which are close in H2 to an eigenfunction of the Laplacian. And the reason they need to do that is because along the sequence of times, they study how the gradients grow and also how the stream function decays. And this needs to be in some kind of very particular balance, and you need good data for that. Okay. So, yes?
T equals 1.
1 is arbitrary, of course.
It depends on the data, I guess.
No. It depends on the vector field. You see, the vector field up to time 1, if you just erase a chunk here, if you erase this chunk, it's a C infinity vector field. So it cannot do anomalous diffusion. Only at the last time can it do anomalous diffusion, because that's when the vector field blew up somehow. At all prior times, it's smooth. It cannot do anything. So if you look at the plot of time versus lim sup or inf, whatever. So if you look at that thing as a function of time, it looks like this. Okay? So it's 0. There's no anomaly. There's no anomaly, right? And then here there's an anomaly. And it's not having to do with the data, but with the vector field. Okay? Okay, so this idea proved to be very popular, and a lot of people worked on improving this construction. I cannot possibly mention all the people, because since 2018 there were probably already 20 papers trying to take this idea and make it more refined. And people came up with very clever refinements of this idea. So let me just mention very few of them, okay? Okay.
So the velocity field is not white in time, but what is it?
In time, it's C infinity smooth in space and time all the way up to time 1, open interval. But closed interval, it's L1 in time with values in C alpha. So if you look at the C alpha norm, it basically degenerates like 1 over 1 minus t. It blows up almost like an integrable rate. Okay? So one of the first improvements was by Kripa, Sorella, and Colombo, Kripa, and Sorella, who basically proved the same result. Whoa, that's far. Same result, but in addition to the anomaly, they got the Obukhov-Korsin regularity. So in addition to getting the first bullet, they also got this third bullet. Okay? It's still just for some initial data. So the statement of Kripa, Colombo, and Sorella are there exists data and there exists a vector field for that data, such that for that data in that vector field, you get anomalous diffusion and the passive scalars are uniformly bounded in the Obukhov-Korsin regularity. And in particular, one of the things that they prove is that along two subsequences, you get two different weak solutions of the transport equation. So this vanishing viscosity limit for this specific data in this specific vector field cannot pick a solution of the transport equation.
Can you, I mean, you already answered it, but all that about this special data, you said it has to be eigenfunctional plus, but I can expand on that because each component will it's a linear equation. It will suffer anomalous diffusion. Each component, the norm is, I mean, everything is additive. So does there in fact exist a single theta that doesn't undergo anomalous diffusion?
Yes. Yes. It has to do with the construction of the vector field. So in this Kripa-Sorella thing, it needs to be self-similar in time. So they start with initial data, which is essentially a chessboard, black and white, which they slightly modify. And then they prove that in time a half, the chessboard at length scale 1 becomes another chessboard at scale a half. In another time a half, it becomes a chessboard at scale a fourth, and so on. So for that proof to work, your initial data has to be really close to a chessboard. I'm not saying there isn't another proof. And the reason I'm saying that is because Kyle Liss and Tarek El-Gindi, a few months later, did prove that for all initial data, so they constructed a different vector field, more in the spirit of that one. And for that one, for all data, you get anomalous diffusion and Obukhov-Korsin regularity. But in all these results, the energy dissipation measure is a Dirac mass at time 1. In all these results. Okay. Now there were these two students at Courant, Elias Hess-Childs and Kiefer Rowan, who proved that if you're happy with this, with atomic time dissipation measures, you can get total dissipation. What does that mean? So they proved that there exists a vector field. There exists U, which is C infinity in time, C alpha in space. Alpha is between 0 and 1. Such that for all data of finite total variation, okay, so think of L1 data, okay? In the vanishing viscosity limit, lim sup kappa goes to 0 of kappa integral 0 to 1 is 0. It's not a half of the data. It's not a half of the L2 norm of the data. It's the 0 constant for all data.
Wait, you didn't mean to write 0, did you? You meant to write the L2 norm?
No, I meant to write 0, hence the word total dissipation.
That's the dissipation.
I don't see a contradiction with what I wrote and what Kiefer and Elias proved. And this is a very nice paper because it shows that if you're willing to go with atomic time dissipation measures, you can get very strange results, like that one.
Glad I'm confused by what you wrote. So you wrote that the lim sup is 0, but you want it to be positive, right?
Yeah.
Say that the energy source is 0.
But we all know what we mean. Just chalk. It's just chalk.
I meant that 0.
Yes.
Thank you, Scott. Thank you. It's a parabolic PDE. So they use actually, this is a really refined paper. This is not a simple extension of Drivas et al., like all the other results are. Okay, so so what Scott and I were trying to do, and I hope I've convinced you by now, is that this point here, which may seem innocuous, is actually not so innocuous. It actually is important. And of course, so is this one. Okay? All right, so I guess it's time to state the theorem. Yes. Okay, so the theorem so we stated the theorem, we gave the proof in 2 dimensions, but I just want to say from the get-go that the hardest dimension to prove what we're about to prove is 2 dimensions. Because in 2 dimensions, there's the most geometric restrictions you can possibly have. In higher dimensions, actually, the problem becomes easier. Okay, so let me state let d greater or equal to, but the 2-dimensional case is the hardest one. Okay. Let alpha be between 0 and a third. Open interval at a third. Then there exists, and it's not that there exists by the axiom of choice, we construct it, right? And these guys have simulated it and done much more with that. there exists a vector field which is C alpha divergence free, weakly divergence free, right? Such that anomalous dissipation, anomalous diffusion holds for all H1 initial data. So all functions of zero mean with its gradient in L2, and with a time dissipation measure, which is it's more than non-atomic. The integral is Hölder continuous in time. But let me just state non-atomic. So if I still have so if you look at the energy of the solutions as a function of time, so in all these atomic examples, the energy is constant, boom, and then it drops, right? That's what happens in all these other examples. So in our example, it's just, and it keeps going, of course, forever. It's exponentially decaying in time, okay? So it's, we do not have that it's absolutely continuous with respect to Lebesgue. It's just you get Hölder continuity. Okay, but the theorem, as stated, doesn't actually do the proof any justice. So let me add additional remarks. So the first remark is about the number rho, which measures how much energy you've dissipated. So rho is an explicit function of a typical length scale of the initial data. So the initial data is in H1. So if you take the L2 norm and you divide it by the gradient in L2, that's a length scale. And rho is an explicit function of this length scale, is a power law. Did I write which power law? Yes. It's a function of this, well, is that, times a constant that depends on dimension and alpha. Okay? So it's not like you don't know how much energy is dropped. You do know, and the answer is that it's an explicit function of the length of the typical length scale of the data. The second bullet has to do with the theorem says there exists U. But that's really not fair. It's not just there exists a U, there's infinitely many. In fact, they're dense in the space of all continuous functions. Okay. The set of all U's is dense in continuous weakly divergence-free continuous functions. And when I say dense, of course, I need to give you a metric with respect to the C0 metric. Okay. So there's not just one, there's a lot of them.
So the rho goes up if the gradient normal goes down?
You see, it's much easier to dissipate the energy of a data which lives at high frequency. So if you mostly live at high frequency, right?
So it seems to go the wrong way.
No, but if you live at high frequency, then you can do unmixed or something. Like you can pick a bad data.
This is what it is. I don't know what to say.
It's easier to have a smooth data because you have more scales.
I don't know. We can talk about this more. All such U's, all of these, are nearly weak solutions of Euler. Of incompressible Euler, of course. What do I mean by this? I've put nearly in quotation marks on purpose. We wrote the proposition in the theorem that explains what we mean by nearly. So there's two ways in which this is nearly. Way number one, so any zero mean divergence-free vector field, you can plug it into Euler, of course. And because you're not so clever as to have guessed a solution of Euler, you're going to make an error. That error is going to have zero mean. So you can write it as a divergence of a Reynolds stress, right? So okay, it's traceless because you can put the trace into the pressure. Okay, so what I mean by nearly is this, is that if you give me an error, 10 to the minus 32, I will give you a U which solves this, where R is less than whatever your error is. Okay, so if you want an error, if you want to solve Euler up to 32 digits of accuracy, sure, we can give you one. Ha, excellent. Thank you, Greg. What is the norm around R? So, another little fact about Euler. If U is C alpha, alpha is less than 1, you have just a weak solution of Euler. Let's say Euler, like real Euler without error. How smooth is the pressure? Little exercise, it's C2 alpha. Okay? There's double regularity for the pressure. Now, statement, this R, because it's essentially, I mean, the trace of it is a pressure, right? So this R should also be C2 alpha, right? The other sense in which this is nearly a solution of Euler is that this norm is stronger than the C2 alpha norm. So it's C2 alpha plus something, delta. Okay? So these are the two senses in which it's a solution of Euler, that it has unusual, basically it solves Euler to leading order, but not to the next order. Next bullet. You see the definition of anomalous dissipation has this limb soup. That could mean many things, but of course what we do is we actually give explicit sequences, right? So there exists kappa j goes to 0, explicit, such that if that kappa goes to 0 along the set union of a half kappa j to kappa j, the theorem holds with limits, not limb soups, not limits, with true limits. Okay, so it's not like these are strangely constructed things. We give you an explicit construction of a sequence of numbers that go to 0. You blow up those sequence of numbers a little bit. So if you send your kappa to 0 along this set, you're actually going to converge there. Now, the other thing we can do, the last, and let this be the last star that I'm going to write, is that if I call this set of this interval I, we can give you arbitrarily many, but let's say just too many, there exists kappa j prime and kappa j double prime, which goes to 0 along I, such that the advection-diffusion equation picks two different solutions of the transport equation. And it's not like there exist, there are infinitely many, such that theta kappa j prime and theta kappa j double prime accumulate on different weak solutions of transport. Which do not conserve energy. And in fact, I hope Scott will convince you of that in one of his next lectures. It's kind of strange to say that they're solutions of transport. They're really solutions of the heat equation, in some sense. That's a more accurate way to say it.
And lambda user are dense and weakly divergent functions?
Well, continuous functions, are they divergence-free? Yes, in the sense of distributions.
Okay.
That's all I mean.
Okay.
That's all I mean. Okay, so that's the theorem. And I guess the goal of this lecture was just to introduce the concepts and to state the theorem. And in the next lecture, there will be like an overview of how the proof should go. In the third lecture, we're going to get our hands dirty a little bit and actually prove some estimates which are at the core of the idea of the proof. But before I let you go and have lunch and half day off, I do want to mention something about this.
You know, you have 4 lectures.
Yes? Yes. You notice alpha is less than a third. And okay, so you may, okay, I mean, in the past many years, 16 years now, or more, there have been a lot of constructions using convex integration, and you may think that that 1/3 is related to that, convex integration 1/3. And it's not quite. So Scott and I want to offer a conjecture about this 1/3. And with this conjecture, I will end today's lecture. So the conjecture is as follows. Let me state it precisely, because if you state conjectures imprecisely, you may end up with theorems. So let D be greater or equal to, of course 2 or 3 is the only one that matters. Assume U let alpha positive, well, between 0 and 1, sorry. Let U be in here. Have 2 properties. First property of this vector field, it's a weak solution of Euler. Incompressible Euler. So in particular, it's weakly divergence-free, and it solves Euler in the sense of distributions. Second property, For this U, the advection-diffusion equation experiences anomalous diffusion for all data with a non-atomic measure. As kappa goes to 0, the advection-diffusion equation with vector field U experiences anomalous for all zero mean smooth data, let's say in H1, with E of dt non-atomic. That was a long statement to write. Okay, so we have two assumptions. What is the conjecture? Then, so this one's going to be very short to write. So it's kind of a strange statement to make, but I think it's one which makes a lot of sense. So if you believe that you're putting a dye in a solution of Euler at high Reynolds, in a solution of Navier-Stokes at high Reynolds number, well, you might as well think that you're putting that dye in Euler unless you think that the dissipative range matters a lot. Okay, let's not talk about that. So I'm doing the ideal mathematical statement, which is clean to write. By the way, there is a Navier-Stokes statement to write here as well. It's just not so clean, okay? And what we're saying is you get to watch, for some reason, you get to reduce kappa, or send the Peclet number to infinity, and you get to watch the passive tracer, and you get to determine whether there is anomalous diffusion. And for some reason, you can do this for all the data, and it doesn't just happen at finitely many clocks. It happens somehow continuously in time. Then the statement is that the vector field you have looked at has regularity less than a third. And Scott and I wrote this in our review paper, and I think the most important thing that we wrote is not the conjecture itself, but the sentence afterwards, which is, okay, the conjecture may be of interest or not, but how you're going to prove this conjecture could be very interesting. Because just think about how you would prove the conjecture. Well, or disprove it. Let's say you want to disprove the conjecture, right? If you want to disprove the conjecture, then in particular, you have to construct weak solutions of Euler that don't conserve energy. Sorry, just weak solution of Euler, forget what I just said, with alpha bigger than a third. You need non-uniqueness, not non-conservation. I have no idea how to do that. I don't think anybody knows how to construct many weak solutions of Euler with alpha bigger than a third. That would be very interesting, though. I'm sure it's also true, by the way, that you could do this. Once you do that, you need to also do this other thing about anomalous diffusion. Okay, that's very complicated. Now let's say you wanted to not disprove the conjecture, but prove the conjecture. Then you would need to come up essentially with an algorithm of how you need to construct. What you get to watch is what happens to passive tracers. Okay? You get to control the data, and you get to watch passive tracers. And out of that, you need to reconstruct what U is, and you need to somehow prove that U is a solution of Euler with this exponent. The pressure makes this problem actually quite complicated. Because, again, we don't want to allow for errors. If you want to allow errors, of course, it's easy. But we don't want to allow errors. And I think such a construction, such a backwards map, I don't know whether to call this an inverse problem or not, would be very interesting to have rigorously done for many other reasons way beyond this little conjecture here.
Maybe in this context, you should mention the paper of Vlad.
Oh, yes. Yes, sorry. Thank you, Scott. So I should say that our there was a very important extension of our work by Sekelihidi, Burksack, and what is the third? Burksack, Sekelihidi, and Wu. Burksack, Sekelihidi, and Wu, who basically said, you know how there was this third bullet, all weak solutions are nearly, all such U are nearly weak solutions. So Laszlo and his postdocs were able to combine this proof that Scott is going to, and I are going to talk about soon, with the ideas of convex integration and a very fine interlacing of convex integration ideas and these homogenization ideas. And their statement then is that those objects in the main theorem are actually weak solutions of Euler. So this nearly weak solution was made into is a weak solution. Okay? And again, they kept these flexibility statements, like the set of all such objects is dense and so on. Okay? So there.
A is not necessary in your conjecture?
No. It is. It is. Because in Laszlo's construction, he still needs alpha less than a third. Right? So if you want to disprove it, you need to go above a third. Right? So I think for alpha less than a third, the status due to Laszlo's and postdoc student, we actually know that you can get anomalous diffusion with weak solutions of Euler. What you don't know how to prove is the third bullet here. So nobody currently knows how to do this. In our theorem, we get anomalous diffusion for all data and non-atomic. In the paper of Burksack, Sekelihidi, and Wu, of course, it's the same. Neither us nor them can get this. So in the regime alpha less than a third, this is the big open problem. That conjecture is somehow independent to this issue. Okay, so there's these two seemingly separate important problems that are open. Okay? And let me stop now, because I think everybody wants to have a break.